Right now, delivering the things people need has never been more important. To all of our Amazon retail heroes on the floor, in the air, and behind the wheel, we want to thank you. We'll continue to do everything we can to keep you healthy, safe, and protected. The work you are doing means everything right now. Thank you.
At Amazon, we're pretty good at getting things done. We're pretty good at solving problems. COVID-19 is the biggest challenge we've had to face. The challenges are what motivate us, like flying masks to our employees around the world. We're doing everything we can to get you what you need, and doing everything we can to keep our people safe. I'm former Navy pilot Sarah Rhodes, and I'm proud to lead our Amazon Air network.
For our first session of today, joining us from India, Alok Gaval, Principal Engineer in AWS, to talk about the foundation of neural networks and modern AI. Alok was previously a part of Amazon Alexa team working on question answering artificial intelligence, and he is currently focusing on computer vision and artificial intelligence. Alok, it is our pleasure to have you with us today. We're just waiting for Alok to join. There you are. Hi.
Hello. So am I audible now?
You are.
Awesome. So I'll just share my screen. Just give me 1 second. Okay, things certainly have to do this at the last minute.
It's okay. It's always nice to have these technical glitches.
Sure.
Great.
Okay, I presume my screen should be visible now?
Yes, it is. Floor is yours.
Awesome. Thanks everyone for joining this session. And it's a pleasure for me to be here at Amazon MENA Tech Conference 2021. What I would like to do in this session is to talk about foundations of neural network and modern AI. So what we will see in this session, there are lots of sessions you will already find on this particular topic online and various other places. I'm trying to give two different characters, two different key messages in this session. One, I'm going to be comparing neural networks to or machine learning to digital logic. So traditionally, we have been doing digital logic design for several decades, and machine learning has relatively become popular. But there's an interesting analogy, some concepts overlap between them that nobody seems to be talking about, or at least not talking about as much. So I'll talk about some of these overlaps, which will help people new in machine learning to be able to correlate how things relate to what they might have known from before. Following that, I'll show how neurons, artificial neurons in particular, are kind of a generalization of logic gates. So we will spend quite some time basically on this one. And what this will again help you see is anything that's digital logic does, right? How we are trying to replicate that with machine learning, just with the difference that we are now trying to teach the machines into doing those things. Followed by that, I'll talk about stateless functions. Stateless functions we always write in programming domain. These are functions that do not maintain internal state. So there are no global variables, static variables inside of them. And I'll show some analogies to see how feed-forward neural networks are actually an extension of such stateless functions. I'll follow that by extending into stateful functions, where there may be some global variables involved, some state which is internally maintained, either via static variables, global variables, and so on. And I'll show basically how recurrent neural networks, which are very popularly used for language processing, including audio, are extension of like stateful functions. Finally, I'll talk about pointers and references, which are very popularly used in practically all like programs. And I'll talk about like how attention in neural networks is a natural extension of basically those like pointers. So my idea here is to be able to show to you that there is these like analogies, and that will not only help you understand machine learning like better, but it will also help you observe some trends in how machine learning is evolving over the time. So first we'll start with this portion on digital logic, how that extends to like machine learning. So we start with considering a very simple function. This is just take 2 bytes and it adds them. So everything looks simple, right? But what is happening behind the scenes is that when the hardware has to go on to add 2 numbers, the logic designers have to go on to design that operation in logic circuits. So what they do is they write something called a truth table. So in this scenario, I'm showing as an example. So every possible bit of B1 and every possible bit of B2 is listed together, and desired output is also basically listed. So this is like semi-manually, this operation is done based on what do we want plus to actually mean. So out we fill manually based on sum of B1 and B2 that we desire. So once the entire table is like filled, so in this table, what happens basically is that every single value of B1 and B2 that we would want the circuit to like exercise, right? We have to basically have this correspondingly entry in this like table. So, and what the algorithm basically then does, this is something you could do by hand as well, but traditionally it has been happening for a large number of like a few decades. So there are algorithms which basically take from this point and try to synthesize like circuit like from it. There's obviously a lot of detail to it, which I'll skip. But one such algorithm, which some of us might even have gone through in our engineering courses, but maybe not, is called Karnaugh maps. That was like used to be done by hand. And there's another one called Quine-McCluskey algorithm, which basically automates that. So trick here is that when these algorithms are designing these like circuits, they must match every single entry in the circuit they're synthesizing. So it cannot be that B1 and B2 are given, and for those combinations, output basically does something else than what was specified in the truth table. Now, these algorithms happen to be basically NP-complete, right? So they're very extensive. As the number of values in this B1 or B2 or total number of bits increases, the optimization to find basically such circuit grows exponentially in size. So result of basically that is that a complex circuit is synthesized, which not only many software engineers, but trust me, like even people who design hardware sometimes fail to recognize that. So they may write basically the plus operation in form of this truth table, and the circuit that comes out from it, they don't basically, it doesn't feel familiar to them. And that's what basically happens when we just write a simple B1 plus B2 in our circuits. Deep inside, those B1 and B2 values are getting routed to that circuit, and the output is read back basically from it. So now there can be like more complex like scenarios where we don't actually need to exercise every possible combination of B1 and B2. As an example, just a simplistic one, let's say we have an enum which has only 3 possible like values, say high, low, or medium. So fourth one is just not there. Now to represent those with bits, we often have like 2 bits, which means the fourth combination would actually be left out. And we don't really care what the output for basically that combination may be, because we don't expect that to ever arrive. Right. So what algorithm basically does, Quine-McCluskey or Karnaugh map or whichever, right? It tries to basically fill those don't care regions. These x-axis are like I'm showing here, in a way that it goes on to use it for something, typically minimizing power consumption, minimizing circuit area, and like so on. And that's an interesting piece. Those are basically unknown inputs to the system. P1 and B2 and out, neither are known. And system is trying to basically fill them to minimize basically some kind of cost function, which is power consumption, chip area, like and whatnot. So let's now look at like a more complex like function. In this case, it's receiving a vector of like 24 bytes, right? And that results in that table becoming like very, very large. So number of possible bits now 24 times 8 is like huge, and that results in as many as having 6 into 10 to the power 2, 1057 entries. By the way, just for a comparison's sake, that's much bigger than the number of atoms in this entire universe. In fact, like for the calculation I remember, you can't even fit that many atoms in the universe, the known universe. So very soon we just had like 24 bytes, that's all, right? And that results in such a huge number of like entries. But if we were to plot all those like entries, it's essentially saying for every input possible that we could receive, we are specifying what would our output be. We can have still more complex like functions. In this scenario, I have like 24 by 24, so 2-dimensional array coming in. And now basically entries is just goes out of the question. Sorry about the typo. There is supposed to be 10 to the power 1387. Right, so obviously our NP-complete algorithms that we talked about for digital logic design or optimization of these like lookup tables just basically don't work. So you're seeing basically now, I think you're starting to get a glimpse of like where I'm going. So we started with some very simple functions, and we could, in theory, start with these algorithms that list out all permutation combinations of inputs and outputs and optimize for those, but it just becomes very soon an intractable like problem. So now this is where the analogy like comes to machine learning, right? So we saw about these truth tables, right? And truth tables are pretty much like training data for these algorithms. In this, like I'm stretching a little bit, but not much. So when I'm basically giving that truth table to my Coin-McCluskey algorithm to find circuit that minimizes power or area or whatever by filling these like don't care like regions, these unspecified ones, right? It's very much analogous to machine learning trying to say, hey, for a desired B1 and for a given B1 and B2, the desired output is with this. So let me try to find some patterns in it, which again minimize something. That minimizing something might be error, or it might be something else, right? So like before, in previously like Coin-McCluskey algorithm that we talked about, it's going to fill these like don't care regions, the x-axis in the table, by something with the assumption that those combinations will never arrive. But in machine learning, it becomes different because we can't actually go on to fill all this table, right? We saw like such a large number of entries that result, right? Since we can't like fill the entire thing, we actually want machine learning to handle most of it by itself, right? So in other words, our cost function isn't just like chip area or power consumption. We somehow want the output to be magically correct, right? But still, it comes down to some minimization, like similarly to what we used like previously like doing. So we'll see basically how output can end up being correct, even in those scenarios where data was actually not known. So that's what. So this is what machine learning ends up being, right? So previously what we saw in digital logic design, we had to specify each and every input and output combination while you're trying to minimize some cost function. But in machine learning, we are saying, hey, we will give you a different cost function such that those outputs, for which the values were not already specified, somehow they come out like correct. And that's the core of machine learning. We just want to be able to generalize compared to the previous problem of digital logic design, where we never cared for how basically that algorithm fills those like x-axis. So with that like overview, where I talked about how there are like the parallels between them, I'll take a deviation. I'll start talking about how neurons are a generalization of logic gates. And once basically we go through that, we'll start building some intuition to the first section I covered, which is how does machine learning, not knowing the entire like lookup table, still basically works out while previous algorithms like wouldn't have. So we'll start like very simple, right? So we'll start with just an AND gate, right? Which is x1 and x2, 2 bits are coming in, and we have to produce basically like output, nothing complex basically like here. What we will try to do is that we will treat that going by the previous like line. So what you see on the left is my truth table. Instead of just using an AND gate, I'm going to use that as again training data for an algorithm, and that algorithm in this case would be a single neuron. So what we see is that I've just plotted basically that truth table in 3D, and you'll see basically shortly like why I'm basically doing that. So what you see is that 3 zeros are basically like here. They are all basically on ground, so to speak, right? While 1 is basically at a height, right? So this is just like AND operation, right? It will become clear very soon basically why we are doing that, right? So now what we want to do is to fit some curve or surface to these like 4 points, right? Again, just bear with me, like why we're doing that will keep on becoming clear as we go. And then we'll tie to section number 1 that we covered, and the whole thing should become like clear out. right? So, but for now, we're trying to basically fit some curve over like surface, right? Now, here's the interesting piece. A plane can never fit. You may try to fit a plane like horizontal one like that, you may tilt it, but since these 4 points are not collinear, they will never basically lie in a plane, right? So that's the trick, right? So plane in mathematical terms is called a like linear like function, right? It's going to have linear function associated with it, right? But linear function actually cannot fit basically these like 4 points, because we have to do something to basically fit that 4th point out there. So what can we do? Well, we can introduce some non-linearity, right? Some of you might realize where I'm heading towards. This is called activation function in the neural network terminology, but we fit basically that staircase, and that goes on to basically fit all 4 points. What else can we do? Well, we have a choice of putting anything in the middle. So we could put something smoother version of it. We might even basically do things far away where our points are not lying. So we may put something else with there. So a lot of different functions can actually be like fit to it. I'm just showing some examples, including this staircase versus this sigmoid. And another interesting one is so-called ReLU function. It's called rectified linear unit. It is pretty much like absolute value. Absolute value basically does a function like this. Here, all we do is that when values are like less than 0, say on this side, we basically force it to like 0. Right, so it's like halfway like absolute value, but otherwise it's kind of like taken to basically like 0. So that's what you basically see in this like plot here. These areas is all zeros, and here is the original value at which it was coming in. And you can see basically there that again you can make such a function and fit basically our 4 points that we're looking for. So what you saw is that there can be multiple such non-linearities we could introduce, multiple such activation functions that we can use and fit our like 4 points. So I'll go over some very basic math preliminaries because not everyone like follows that, but it will I think become very clear like what's going on. So in this scenario, what we have is 2 variables x1 and x2, while they're actually bits here, right? So they are not like continuous values. We'll treat them as continuous values nevertheless, and we'll see basically why we are doing that, right? So what you see is a line there, which is x1 plus x2 equals constant. So reason why sloping downwards like that is because if you increase the value of x, then same constant is reached by decreasing the value of x2, right? So they're sort of like going opposite to each other, right? So that's how we'll basically plot all these like plots where we're trying to get a constant value basically out of it. So let's now look at what happens if I change that polynomial x1 plus x2 to 2x1 plus x2. So what you see here is that this line becomes like more vertical. Why is that? Because now half the value of x1 is needed to reach the same constant output. Right. So previously, if x1 needed to be 2, to basically for a given value of x2, x1 needed to be 2. Now x1 equals 1 will basically do the job. Right. So changing these coefficients of x1 and x2 are moving basically the slope of the like line around. Similarly, we can do still more, right? So I'm modifying the polynomial even more. So it's now 2x1 plus x2 minus b, right? So what minus b basically is doing is that sort of reducing the value of the left-hand side, right? So what that means is that x1 and x2, that combination needs to become higher in values, right, before the same constant is like realized. So what you will basically see is that as we are changing like these coefficients, 2 or 1 in this case for x1 and x2 respectively, or b, our curve actually like moves around. So I'll now show the same thing in like 3D, right? So it's gonna basically looking like this, right? So same function basically as before with the sigmoid basically smoothened out, right? And I'm basically changing like b. So what you see is that as we're increasing b, that curve basically is like moving up in terms of x1 and x2 like value required, right? Same reasoning as what we like saw before, right? So now x1 and x2 need to reach a higher value before basically that constant value is like realized. So changing W1 and W2 in a very similar fashion. Well, in this case, I can't change W1 and W2 together. So I'm changing them in a way that their magnitude happens to be constant. So you see this curve like rotating. So W1 and W2 essentially are controlling the direction, the slope in which basically this like curve like lies, right? So we again saw the line, and when we change to 2x1 plus x2, you saw basically that curve like shift. That's exactly what is like happening here. So with these basic math preliminaries, here's what we now have, right? So we had our equation as wx1 plus wx2 minus b, right? And we are passing basically that value through a nonlinear activation function, which you call sigma. So essentially then b is controlling how far from the origin that like shift that either the staircase or the sigmoid like slope that basically lies, right? And W1, W2, and B, so B, they're just controlling basically what direction basically this thing like lies at. I'm approximating a little bit, but this is still the core concept, right? While the activation function we use sigma here defines the shape, whether it's staircase or whether it's this sigmoid and like so on. So that was in 2 dimensions. If we have like more than 2 variables, say x1 to not just x1 and x2, but x1 going to like xn, are still basically very similar, just that we extend the formula very same. I won't even like talk basically much more about it, but that's the core idea. Nothing else is happening. So that becomes the equation of an artificial neuron, right? Is that x1 times w1 minus because some bias, and it goes through some activation function. So let's now basically look what we are trying to do. So we were trying to take this like truth table that we had for an AND gate, where we had 4 basically like values, and we want to change that w1, w2, and b such that our function actually like fits. So what you're seeing on the left hand side here is I have chosen basically w1, w2, b such that all 4 points like fit, right? So no error. Basically the curve that we are having is going through all 4 points, right? But on the other hand, here I've changed the value of b. It's like smaller, as you can guess, right? And that's basically goes on to miss out basically those 2 points, right? So essentially what we're trying to do is we are trying to basically take this shape, the function of a neuron, right? Whether it's staircase or sigmoid and whatnot, and we're changing those parameters w2 or w1, w2b such that basically our error is kind of like minimized. And that's the core trick, right? So we're trying to basically make our neuron effectively learn that like truth table that we provided to it. So likewise, you can see left hand side is still basically good. On right hand side, now instead of staircase, I have basically the sigmoid. But now, given the values are on the y-axis, height is also like continuous. It can result in basically like error which are not just like 1, but it's still being suboptimal on the right hand side, because as an example here, there is still being some error, and likewise maybe a little bit here. So now what we will see is that what happens in the error against that truth table as we go on to change like b. So what you're having here is error is going with like b. So I'll just rechange that, right? So as you see, as I'm increasing b, my curve is shifting upwards as like before. And at some point in time, my error basically actually goes on to 0. And if I keep on increasing b even more, my error actually like increases, right? So only when this step happens to be in this range, error is 0. Otherwise, error is basically like some number of bits are like actually like missed, right? Similarly, we can do against w1 and w2. So I'm again basically rotating this like staircase around, and you can see that error is kind of like high here, but at some point basically error like goes on to reduce, right? So essentially we have to change this w1, w2b such that our surface that we are like finding goes on to fit basically that like truth table or training data. So essentially, we had very simple scenario here, which had just an AND gate, which had 3 parameters, right, for the neuron, right? And we already basically see that to be able to optimize basically it, I showed the graphics where either I was changing B or W1 and W2, and even within that, I was changing W1 and W2 sort of like together. I was not exercising those independently. Why? Solely reason that otherwise I need basically 3 input parameters and 1 output, so it becomes a 4-dimensional plot, and it becomes hard for us to like visualize. Right. So in this particular case, just so happens that the optimum I showed happens to be the like best optimal point. But just by looking at these like weights and changing them independently, we are not guaranteed that we'll actually hit an optimum, because it's not exactly a linear like problem. So that's what happens. We can't like manually go on to do this, what I just did in last couple slides, for a like very large number of parameters. And we saw kind of early on in section 1, the number of parameters can become so humongous that is like just goes out of like whack. So what we thereby need is some kind of iterative method, right? And this is where basically I'll start drawing the connections again from the digital logic design or lookup table, basically like based computations, to what machine learning does. Right, so we can't basically go on to handle such large number of parameters like we saw for a face coming in, a 24 size like byte like coming in, right? We can't basically handle that, right? So what we can try to do is to find some iterative method that says, hey, let me guess the values of W1, W2B or whatever other parameters like are, right? And then basically if I can somehow know how do I change those to make it better, that basically could be a lot more effective rather than having to analyze the entire basically like table for all different possibles of these parameters. So that's what basically like shown here. So you can, we are trying to basically start with some guess for these like parameters. This is often taken to be random guess, but there are some guidelines around that too on how do you choose between those random ones. right? And we are basically trying to walk in this hugely multi-dimensional space. Like as you saw, there might be like millions or billions of like parameters, right? So, but the way you can think of it is that we can't like visualize that entire space, even in the 4-dimensional case that we just saw. But now we have like billions and billions of dimensions. We can't basically do that, right? So what we're essentially trying to do is that we're standing at a given point. So we are saying, hey, these were my W1, W2 Bs or whatever values of the parameters were, right? Let me evaluate two things there, at least two, right? One is how much is the error at that point in time, right? But second, I want to try to evaluate what is the slope. Here's the analogy I give out, right? So imagine you're standing somewhere in this like mountain region, right? So when you're standing, from your feet itself, you could actually feel which way your feet is like aligned. And if your feet is this way, you will try to basically walk in that direction, right? If your feet is like this, you will basically go in the backward direction. So you basically not only know like what error there is, which is the height of this like plot, but you also get a sense of derivatives that tells you basically in which direction you should go to reduce the error. Right? So in this space, you can't really see around. So you're walking pretty much blindfolded, but just by knowing your current position and somehow you know the current height as well, right? And seeing the slope, you just keep on basically falling here and there, right? So that can obviously result in some issues. If we start from here, we end up reaching that like global optimal point, which means we find the best like possible weights that fit our like truth table in this case, right? Similar thing may happen here, but at this point in time, it might, instead of falling here, it might actually have fallen basically here. So we need not reach the best possible state. We can get stuck in so-called local minima, but I won't talk a lot more about that. Our target is to basically find a good enough function that actually like goes on to fit. So now here was the trick, right? So previously we said we will try to look at the slope and like walk around basically that space because we can't basically. One more thing I want to like mention, interesting piece, right? So this is I think one very interesting thing when we see. Right, so we had millions of those like parameters, right? And that entire space we cannot actually like exploit. We cannot keep on looking like all over the place, basically like that, right? So by basically changing to an iterative method where we start with a given location and we keep walking around in this multi-dimensional space, but we are not exploring the whole space. We're walking around just like some curve, right? So thereby we have turned the problem of having to analyze that entire space, which is what that Quine-McCluskey algorithm would basically do, right? To basically sort of like movement along one basically path, right? That path need not be straight line, so it is still multi-dimensional, but still basically just one path in that multi-dimensional like space. We don't have to analyze like everything, and that is the key thing that results in that change from basically those NP-complete algorithms we had like before, which we could not basically like track, to basically machine learning, where by following basically this slope, following this iterative method, we cut down the amount of computations by orders of magnitude. Right, so million dimension space basically there to basically sorting just one path in that space, right? And why that works out? It works out only because there's some smoothness assumptions in that space, right? It need not be fully smooth, but there's at least some smoothness, right? So if we were to fill the lookup table, we could fill it in arbitrary fashion, right? Every output could be made basically random, in which scenario there may not be any basically like smoothness in the space. Like one for a given like input, if you know the output, that does not tell you anything about another basically inputs like corresponding output, right? But here in real life, when we are trying to do machine learning scenarios or detect a phase, that's not the case. We have smoothness basically inherent in there. And that's why this iterative method actually goes on to work out, and it reduces the amount of compute we require by orders and orders of magnitude. So trick now is basically that we can do that, right? As I'm assuming this smoothness is there. But when we used this staircase function, you notice that no matter where we are standing, we are in a flat area, right? So basically, like just by feeling of what the slope is looking like with our feet, it actually does not basically really tell us like which direction should we move to. And that's why basically for neural networks, we just use staircase function, which is called perceptrons in older terminology. All the people are like trying to use it in different ways now. Right. So basically it doesn't easily like converge. It's hard to basically get that to find basically that solution because the space is smoothness input problem at smoothness. But just by using that staircase activation function, we basically killed it. Going to sigmoid, let's see basically what happens. Again, we are doing exactly the same thing, but error basically is like moving around in a smoother like fashion here. So we still have flat areas. So if you're here, we wouldn't know basically where to move. But if we happen to be in this like slopey area, then we know basically where to go to try to reduce the error. Right? And that's why sigmoid actually works a lot better than staircase like functions. Let's now look at the same thing. This is now done in W1 and W2. So again, you see there's smoothness that results in that like space, right? So, but still lots of like flat areas, right? Let's now look at what happens with ReLU, right? In this case, because we changed to basically such a like function, right? So error basically tends to stay there. Flat areas are like avoided. That's the key thing, right? So you don't see as much like flat areas here compared to what we saw in the like previous slides, right? But still it could basically show up, right? So you see here that these areas became very smooth. So if we happen to be here, we're pretty much like guaranteed to get to a local minima, right? But we still have lots of flat areas because after all, we had a lot of flat areas like here as well, right? But what happens is that when you, this is like just one single neuron, but when you have like very large number of parameters, right? These different like neurons, which all be basically putting their ReLUs in different like shapes and sizes, really like that, right? So even if like for few of the ReLUs, we happen to be in that flat regime, for some other basically like neurons, we would end up having basically in that like slopey region, right? So for in either way, we end up moving a little bit around and we keep on basically finding our like optimum. So this actually shows like why ReLU function works much better than the previous function we saw sigmoid, and it has resulted in basically this like evolution like happening. So now we'll assume basically that whichever function we were using, ReLU or like sigmoid or this thing, we have found basically our optimum. So we have like taken the very hello world kind of problem where we had AND gate, the truth table coming in, but we trained a machine learning network, single neuron basically with it, and it has to be found its time. So now what happens basically is that like C, right? So very same neuron, if we had an OR gate, which is shown on the left side, like just by changing that B, you can actually realize that OR gate, right? And if it is a NOR gate, right, it's a little bit tricky, but you have to just change the W1 and W2, rotate them to basically face the other way around, right? But it still basically goes on to like work, right? So what you see is that simple OR gates, AND gates, NOT gate, NOR, right? They can be basically realized by same function of a neuron. So very same neuron can replicate basically all of them, right? There are some caveats. Exclusive OR is a little bit tricky. I won't talk about basically that, but feel free to like search on the internet like for it, right? But even exclusive OR can be realized, just it needs like more than one neuron, right? But imagine basically now this thing. So some of you basically may know like Boolean expressions or like logic circuits we have. If we can synthesize AND or a NOT, then any combinational digital logic can actually be synthesized, right? And hence anything that a combinational digital logic could actually do, a neural network can also do, because every gate is essentially a neuron, right? So that's one of the core things I want to talk about, right? So very interesting thing like happens, right? So we use, typically we use neural networks implemented on top of digital machines, right? But anything a digital machine can do can be done by neural network itself, right? So we sort of like have an interesting thing I'll talk about like a little bit later. So let's now say basically what happens if we were not having all basically points. We had like just 4 points in our AND like operation, but we had like more of basically them, right? So under this scenario, like the single neuron will try to make a prediction, as in basically what exactly would like happen, right? And this might have basically actually some like use cases. Just to give you very simple, again, hello world kind of example, right? Let's say my variables input x1 and x2, assumed to be continuous now, were capability and motivation respectively, right? So if I am basically highly motivated but I'm not capable, I may not succeed, and vice versa, right? So both of them are somehow needed together for me to like reach success, and this neuron can basically like want to learn such like pattern. So what basically happened so far is that since our input basically function were like linear, W1, X1, W2, X2, minus B, and so on, right? So a consequence of that is that even though we have curvature via this activation function basically like this along the Z, but this edge by itself where this curvature like happens is bound to be a straight line, right? So there can never basically go something else, because remember like when we saw that, like W1, W2, B are changing basically where that line is positioned, right? And it changes how this curve acts along that, but it always remains a straight line, right? So what do we do if our data is like more complex, right? So here I'm showing a 2D plot, right, where my values are more complex than an AND gate that we saw before. But let's say this is our new truth table or machine learning training data, whatever we call it, right? So all the ones are here, also zeros are here, which I'm again shown in the 3D. So these are all the clump of all the ones, and this is where all the zeros are. Right now, I don't have a single line that can basically go on to like partition them. But what I can have is that there can be two neurons, one basically that lies along this line and second that lies along this line, but they will both get something wrong, right? So this is exactly what you see. First neuron is basically able to fit these and these points, but these ones are left out, right? Because well, it can't basically go on to curve like that. Neuron 2, I can basically go on to put on the other side, but it leaves these other points out, right? So again, when we basically had that sloping happening along a line, then we can go on to fit in a single neuron. But if there are like more basically variations on that, if it's not a single line or a hyperplane, then we basically don't fit. But see what has happened basically here. When I put basically neuron 1 and neuron 2 both together, when the value the output is high, 1, right, they are both right? So they're wrong only when basically values are 0. So essentially what is there is that if I basically take those same x1 and x2, I pass these two like neuron 1 and 2, right? And I take the output of those neurons. So remember, that's not x1 and x2, it's the output of those neurons. My third neuron just need to AND them together, right? Because when first neuron says point is high, second neuron also says point is high, then it actually happens to be high, right? So that's what basically like results. So we kind of like taking those 3 neurons, we were able to synthesize that peninsula-like shape, right? Which we could not have done with a single neuron. Right. So what you basically insight I want to give you from here basically is that no matter basically what shape comes, right, by fitting basically those like lines here and there, you can actually go on to synthesize that with a neural network. And here's the intuition basically how it might do that. So now in this scenario, we going from like single neuron, we now have 3, N1 and N2, and N3 where in this example is just serving basically like an AND gate. Now, reason why we basically, remember I talked about the input space of the problem needs to be smooth, right? If it is not smooth, if like one input does not help you infer anything about another input, right, then basically this gradient descent type of method would not work, right? So that's why in machine learning, it becomes very important that equations we use actually are differentiable, right? So staircase, when we took, it becomes like hard for us to basically like go around basically that, right? When equations are differentiable, when there's smoothness basically there, then machine learning ends up working as far as the input problem basically is smoother. Let's now take still more complex example. Previously, we had just like 2 edges along with this line which could like handle this peninsula. But what if we have like circles, right? So I want say 1s here or like 0s here. How do I basically do that, right? Now notice that here the training data does not specify what to do basically in these like white regions, either here or here. Right. So if I were to give this training data to a neural network and I was to use similar basically methodology as I described, I might actually position those 6 lines forming a hexagon, right? So I can position those 6 neurons just like that, right? And then again, I have an AND gate residing on the top, right? So 6 + 1 neurons can actually go on to approximate basically this like fairly well, right? Of course, it worked because I had like this white regions in the middle, which allowed the hexagon to be able to distinguish like these two. Right, but if I have like lesser gap, I'll end up needing just more neurons. That's all that happens, right? So if you were to actually like run this exercise and give it to the machine, you end up finding that it's able to use just 3 neurons, not 6, in that basically middle layer, and able to be separate them. Essentially, it has found some triangle which like fits like good enough, something like that, right? So what has happened basically now is that what you see in this 3D plot, right? So remember, like what we saw like here, we took the output of neuron N1 and N2, and that was the input to neuron 3, not X1 and X2 alone, right? Similar thing here. Now we have found 3 neurons, and they are all the output to basically this one. So when we look at the perspective of this particular one, there are now 3 independent variables. So that's why it's 3D plot here, right? And what these 3 neurons have essentially done is that they have basically separated these red and blue points along the 3rd dimension. Here they were all lying in a plane, right? But they have been now separated in the 3rd dimension, which allows a basically new plane to fit in. Right? So this neuron, again, as we saw before, it can only find a line or a plane that separates basically there, right? So, but these neurons have modified them so that a plane basically fits, and thereby basically system is able to learn. So we can go on to create more complex shape. This is an interesting homework exercise I like to give out. Previously, we had the circles and peninsulas and so on, but what if we have world map? So example problem I have here is that given latitude and longitude, right, you have to write basically some code or some machine learning algorithm to predict whether that point lies on land or on like water, right? So interesting exercise, like, but again, you can imagine basically there, by fitting basically those like different lines basically in, system would be able to partition the space into basically again land and ocean, right, land or like water, and be able to say, hey, given latitude and longitude, whether it's like which one basically it is on. Right. So with that, what we saw is that let's actually look more, right? So we now bring back those like complexity like we had before, right? So we had 28 by 28 bytes, right? And my basically chance is to find out basically whether it's like 4, it's 104 or basically not, right? Now it looks like a 2D image, right? But this is a different example. Previously we had just 2D, two input parameters, right? So our space of basically we're searching was like 2D, right? So the world map still considered latitude longitude, just two inputs, right? Here our image is 2D, but the number of parameters coming in is still basically very large, right? 28 by 28 like bytes, which is huge number of bits. Right. So again, if we were to go back to that Coin-Mikulski algorithm, where smoothness was not assumed, and thereby would have a hard time solving for it, and just give up, go home. Right. But machine learning with that smoothness, because even if this 4 shift little bit, increases size little bit, tilts little bit, right? So it still basically remains a 4, and that's what basically produces that smoothness, which allows machine learning to basically like work there. So essentially, what we have now is that we take those 28 by 28 like bytes, we feed into that resulting. Everything is going into like input neuron, right? That becomes just an input. Right? And let's say we have this hidden layer. We start with 100 like neurons. Now, previously we started by basically saying we had 1 neuron, then we had 3 neurons. Here we are taking some guess, and we might be try to like iterate based on what number of neurons we might need to fit. Right? Now, ultimately, again, just looking at the same thing as before, given the smoothness and given this iterative method, it will end up basically finding, hey, when is this given input 4 versus like not? Right. So again, these are changing the space in like some way, such that this 4 last neuron can find a single plane that separates out everything that's 4 from everything that's not 4. So exactly. So that's how like handwriting recognition, or basically like digit recognition, actually like goes on to like work. So now if we have to recognize like all digits, right, we can basically just repeat the same thing for every digit. Right, it would actually like work. It is nothing basically that would not work, right? But what we basically typically do is that instead of basically having a separate like network, which is having all these like neurons like repeated, right? We try to basically make the last one like separate, but previous ones we try to really share. It's essentially like this is telling 0 or not, this is telling 9 or not, right? But previous neurons basically may be shared. Why we do that? Well, because like we have like given amount of training data still for which the inputs are known. Right? And there are patterns which like are common between basically like 0 and 9 and 6 and 8 and like so on. So system is able to make use of those to be able to basically like find those patterns here, which feed into whether telling something is 0, 9, 1, 8 and so on. Right? But what is happening here is still this. So this is again just taking 2 of those 784 inputs. I can't basically plot all of them otherwise, right? So you have to just take 2 of them. Basically there, like 2 pixels are not enough to tell me whether it is something is 0 or not. Right? So that's why basically here what you see is that these different digits which are color coded, they are basically all like jumbled up. After 2 pixels won't tell us anything, right? But when we go from here to basically this like hidden layer, system has tried to basically change it in a way that is trying to be separate with those out. Right? So that's how basically going further layers down, if you want to identify just like say 0 or not, maybe 0 is this like green clump. So it's gonna be able to basically again draw those like boundaries around that and basically say, hey, it's 9 versus 0 or not. Right? So that's how neural networks are like doing basically that like magic, as you saw before. So far we saw basically like numbers like only. What we will basically do now is we'll talk about how do we represent discrete objects. So an example could be like words or human beings or like whatever objects we have. Right? So we start by doing basically one-hot encoding. What that basically means is that let us take an example of like say English language where we have we assume there are 10,000 like words. Obviously there are a lot more, right? So but we assign basically one hot like vector to each word, right? So this means is that when the like say word is a she, right? We have a particular like number in that which we make 1, everything else is a 0. So if you have 10,000 words coming in and we have 10,000 basically numbers, right? Each word will corresponds to like one basically particular like index in that, right? And every other basically value we make a 0, right? So this is called one-hot encoding. Obviously you can see it's very inefficient, right? So if we had like the 10,000 numbers, right? We probably needed, I don't know, the 15 bits to encode that, right? But let me be less, right? But we basically use like a lot more basically here, right? So we start out basically by that, right? But we'll see basically what's going on, right? So what we do from basically that is that using this one-hot encoding, we can represent objects as numbers, right? It becomes a very large like space at that point in time. But so far as we saw, we've already found a way to basically deal with this large spaces. So using neural networks like itself, we start with such a large number of numbers and we basically go on to do the same magic. Very large numbers, it reduces to smaller number of numbers and like so on, right? And we're able to find better representations than that one-hot encoding. So this is how basically the embeddings that you might have popularly heard about for different objects basically are like found. So word to vec is an example of that. So let's now say like we have still more complex like stateless like functions, right? So I'm computing this quadratic like value with a, b, and c coming in, right? Now I end up basically what I could do right in this scenario, right? For again, just like we did for plus operator, we could basically go on to do for all a, b, c basically like values, right? And be able to basically synthesize using that Cohen-Macaulay algorithm a hardware instruction that solves quadratic equation. Right. Remember, just as we were writing plus basically there in the code, it actually goes on to some hardware to like get me the results. Right. Same thing could be done for 3, 4, 5, 6, whatever number of inputs. We were not doing that just because it goes interactable. Right. So, but what we do instead is that we basically got couple functions like square root, basically square, like multiply, add, so on. Right. So we devise those in hardware, and then you use a sequence of those to basically synthesize like our quadratic like solution. Right. That's not very different from what actually like we will do in neural networks, as we'll see, right? So in basically like hardware, what happens is that just by having any Boolean expression, it can be synthesized into just and or combination, right? So either and followed by or followed by and like so on, right? So in a similar way, just from the analogies we basically already built, any complex function we might basically have, right? So whatever complexity is that, we saw some like a world map or like 3D functions or like any number of parameters, right? For exactly the same reason, right, that for which like two-layered logic gates is always enough to synthesize any combination logic, same thing applies straight away to big neurons, right? There's more formal mathematical proof of it, but intuition is like no more complex than that, right? So any basically such shape can be synthesized with a neural network, and that's how basically we are finding magically like more and more machine learning problems we give it, it's ultimately able to be like learn, even though we don't fully understand how and why the learning process happens. But we know basically a solution is like certainly like possible, right? So just like what we saw here, now instead of like synthesizing quadratic as a, like one single instruction, I basically use a series of basically these computations to represent it. Kind of similar things happening in deep neural networks. Even though 2 layers of like a network was like enough, right? We synthesize like multiple layers because they are able to share the pieces, the intermediate combinations, right? So B computed here is used here as well as here, right? So such basically intermediaries automatically get learned by these like layers, such the system basically goes on to compute. But the analogy I'm drawing is not kind of exact, right? But it's similar basically to that respect, that multiple lines of code are going to compute something. Similar way, multiple layers of deep neural network are going to compute something, right? And as we saw, kind of these intermediate variables which are like involved, in a way of speaking, basically these go on to learn those intermediate representations, right? So essentially then any stateless function that's going to n number of lines of code, right, could be represented by a deep learning network. It could have been done with 2-layer as well, right? Just like we could synthesize that quadratic equation with like, again, discrete like hardware, right? So, but we can learn that. I'm not suggesting basically that n lines of code should map to n lines in a n layers in a deep neural network. That's not my intention, but the analogy basically still like valid. So we saw basically X number of lines of code in a stateless function like quadratic, where there's no static variable, member variables, or like global variables involved, right? Can be done by this feed-forward neural network, which may be basically deep or like shallow, based on what the problem is, right? So let's now look at what happens when we have stateful functions. So here's an example. So I'm having this function which computes like average so far, and it gets not the entire array together, it gets byte at a time, right? So it has to return average so far. Now, obviously, it has to maintain some internal state because unless it remembers all the byte values we receive, it cannot compute average so far, right? So what we can basically simply do is that we introduce these two variables. I put them as global in this scenario, accumulator and count, right? They are maintaining what is the total sum received so far, total number of variables received so far, right? And at each point in time, it returns that like ratio, which is the average so far. Now, one more byte comes in, we adjust these two values, we return next average so far, right? So essentially, we have a stateful function, which has to remember that accumulator and count, right? Exactly similar way, we do it in recurrent neural networks. So what is happening is that our X variable, which is the byte here, is going to that neural network, but we also have that accumulator and count coming out from here and feed to the next iteration of the very same thing, right? So that's the key, right? So this neural network, I mean, here we basically have the logic here, which is accumulator divided by count, right? And this plus operation here, right? If that were to be learned by neural network, essentially has 3 input parameters, accumulator, count, and B. Just that 2 it's storing in itself. B is the only one which is like coming from outside. Similar thing is happening here. This neural network will have to learn how do you take basically these 3 parameters, 1 byte coming from here, 2 accumulator and count coming from here, 3 variables, and generate basically this slash h, right? So it's learning basically all of that. And it's also basically learning how do you produce new accumulator and count from basically at the output to feed to the next iteration, right? So essentially, basically, a recurrent neural network is implementing a stateful basically type of like function, right? Just that the math involved, it has to be learned. Now, trick would be basically that just as here we put accumulator and count in some global variables, right? In neural networks too, that's what exactly we would have to basically do, right? So that function we are synthesizing, that A function, it basically spits out those like accumulator and count for the next iteration. We'll hold them in memory just like we would for stateful like functions. No, nothing different. Why? Because our neural networks so far, it can learn things, but it does not have dynamic memory into it, right? So in terms of implementation of this neural network, we will need a stateful function to do that, because this memory we still need to keep. Right? Now, how basically learning in this case happens, basically is like, I won't go too much basically into it, but learning has to propagate back in time, because like when we start with the very last like output, right, it tells us basically what the input and the accumulator and count need to be for a given basically like level, and it has to go back in time, because system otherwise does not know what should have been the accumulator and count computation for like intermediate basically like levels. So you have to unfold this entire thing, and that back propagation happens for like every basically like layer. So using basically just that, right, the magic basically like happens. So what we might basically do is that this is now that long neural network. We basically feed in different like words getting in here, right? Just like we were feeding those bytes to compute average so far, right? Here we're feeding different words, but we are making it learn something, right? Which is a representation of a sentence, right? It's a vector. It's just a set of numbers, right? We can't easily see what exactly that's basically doing, right? But we can basically synthesize that, right? And then basically, whatever it outputs, we're feeding the same thing here. We're feeding the same thing here, just like what we saw before. And we can go on to basically train it to produce something else at the like output, right? Now, in these scenarios, we could make it arbitrarily complex. It could be input waveforms coming in, like audio coming in, and we want output to be text, right? It could be output to be different language altogether. It might be strings coming in, right? And just by basically giving that training samples, right? Because we know there's some smoothness expected in the space, right? By using these like neural network techniques without having to synthesize like that entire lookup table, we are able to basically do things even as complex as language translation. That's the magic, right? That's the piece where some theoretical questions are still there, and how come basically we're able to learn basically that, right? But this is the intuition. It's just finding that like optimum that works like good enough. So now here's even more. When this thing actually first came, it was like surprise to me. I first heard about this thing in like 2013. News were coming out, hey, like you feed an image to a neural network, right? Deep neural network, right? And it describes in English what is seen in that basically like image, right? So I was totally shocked. Hey, if I were given this problem, basically, hey, Alok, go basically like do this thing, right? I was clueless basically how I would have done, right? But theory behind that turns out to be like fairly simple, right? What we had was just like we saw that digital recognition, right? We're feeding basically that image and producing basically this like intermediate representation. And that intermediate, we feed into a like this type of neural network instead of feeding accumulator and count. It's like more complex, basically vector like fed in, but it's basically fed into that, and it produces basically some language out there, right? So obviously we have to do some impedance matching here. We have to train it basically together, right? But kind of that's the concept, right? You start from an image, you're computing with something with a neural network. It finds some basically representation, better called an embedding. Like that embedding you feed into this recurrent neural network, which has the state, and it keeps on producing like words at a time. And just by that, giving lots of training examples, given some smoothness assumption, right? Which is obviously true. If I were to add one more vegetable here, probably my string would not need to change. That's the smoothness like aspect, right? So system is able to basically take an image and auto caption basically it. So let's now take still basically more complex examples. I think we are coming towards close of it. I'll be done very soon, right? So basically we have say cursive handwriting, right? Sorry, my font got messed up. Say I'm basically writing basically in like with handwriting, right? So what's typically seen is that I might write like I, then N, and then G, and I may place that dot like after finishing this up. So after I write the entire handwriting up, I place this dot later, right? So this long range relationship. Right? In what we saw in that average so far, basically we didn't need to have any long relationship. We basically have this current variables, current state, right? And from that itself, we can always go on to produce the like answer. So relatively easy, right? But let's look at another example where we are really sorting numbers, right? So if I were to basically take all these basically as inputs and feed into basically like here, I somehow am expecting my representation here to be sort of like knowing in which irrespective of which order they came, what all numbers came, right? So if I have a very long like array, somehow it's kind of like not seemingly like seems enough that we just sort them just with this algorithm, right? So in theory, yes, it can. If you have to like guarantee that number of symbols you'll receive is just like finite, say 0 to 10, right? And number of like the size basically of this like array is also like finite, right? You could actually train that neural network to basically sort, right? I think it has been experimented with as well, right? But basically, like in general, when inputs can be arbitrarily wrong, sorting becomes a harder problem than average so far, right? So under that scenario, what happens is that just having that state memory, like we saw in that accumulator and count, does not turn out to be enough, right? We need some sort of like random access, right? And that's where like pointers basically came along, right? So like imagine basically like practically any algorithm we do from very simple like ones like sorting, right? We have indices to those arrays and we are manipulating those I and j to basically like do things, right? So that pointers were basically there in like our software coding from like kind of hello world kind of programs, right? In machine learning, so far, so much we discovered, right? So much we talked about neural networks, like recursive neural networks and so on, right? We never had pointers basically there. So this, in fact, used to be basically one of my questions back in like more than a decade back, saying, hey, like my brain, right? So it was basically well known at that point in time that anything a digital logic can do, a neural network can do, and vice versa, right? So anything that the neural network can do, we obviously run those neural networks on top of our digital computers. So obviously that applies, right? So my question was basically, hey, when my even simplest of the algorithms need those indices or pointers, right? What is my brain doing? How is pointer basically represented here, right? And I had some ideas around basically it, but basically soon somebody else did it like before me, right? So this thing called attention in neural networks is basically like that. So this came from a paper that came along some time back, I think 2015 or something. Attention is all you need. So what it basically said is that if we were to basically have attention, we don't actually need that state, the thing going around, right? Why? Because as I said, attention is kind of a generalization of pointers. And with pointers, if you can actually look at every single like input, why do you basically need to like maintain a state? You have everything in memory, right? So I'll give you an example basically like of how basically this thing is happening and how attention is sort of a generalization of pointers that we had before. Right. So imagine basically this sentence, courtesy of like Google. It says this animal didn't cross the street because it was too tired. Right. And second variation of it, it says it was too wide. Right. Now here's the trick. Right. If it is tired, it's not the street, it's an animal. Right. And if it is wide, it's probably not the animal, it's the street. Right. So just by looking at the last word, you basically like you need to know that before you can tell whether it points to street or animal. Right. And in fact, our neural network would even have to learn that it does not basically map to cross the, it was, and so on, right? So basically, it has to learn all of that too. For us, it's obvious it is representing some of those like entities in there, right? So now basically what happens is like if you were to resolve basically this thing, right? If you need a pointer, it can either point to animal or it can point to street, right? Pointers basically don't refer to multiple things together, right? So here what we do is this is how we generalize pointers into this so-called attention, right? So we make this pointer go say 0.8 to this, 0.2 to this, 0.01 to this, 0.03 to this, and so on. Like essentially, since we have already converted those like words or whatever objects we have to numbers, right? So we computed weighted sum of basically those, right? Now, if those weights just happen to be 0, 1, 0, 0, 0, well, that's a pointer, right? Then it basically takes exactly the same values like here, just like what our pointers do, right? But by adding this like weighted sum, we have sort of like generalized it, and that is exactly what is like attention. So when the system is basically reading this thing, when it reaches basically this we actually find in these neural networks once they're like trained that it's basically paying attention to basically this animal and street, but it doesn't know the answer, right? But when it basically finishes the sentence, at that point in time, it basically knows, hey, this is street is more likely, and here like animal is like more likely, right? So attention in network basically there is doing that, right? Now another aspect basically of that, another way in which same thing has been basically done, right? Instead of using a weighted sum, right? What we are basically doing is that we are saying we will take one of these elements only, not basically weighted sum, one of these only, but probabilistically. So probability might be say 0.8 for animal, 0.2 for like street, and 0 for everything else, and like whatever, right? So probability, right? That one is also basically surfaced up in the very recently in the machine learning circle, and it's called pointer networks instead of like attention networks, right? But you can see basically how we are trying to get pointers that we have always had in programming again into neural networks, right? Now, where this is done, I won't cover in basically detail, but core thing is that these weights, how do you generate basically those? that also depends on the inputs. So basically, like previously we had only the inputs and outputs as like variables, while every weight that was there in the neural network was just learned during training time. During inference, those weights don't change. But here we have these new weights which need to change during like inference time as well. So what we are basically essentially doing is that we are having another like neural network which is learning to generate those like weights, right? And this is how one nonlinear operation again comes in. So input is going via here, but weights are also basically being generated by another neural network, right? But that's all. That's all there is to do it, right? So with that, again, by taking large amount of training data, with suitably large amount of training data, we are able to basically make it like learn attention. And now it becomes a homework exercise to try to see, hey, could you basically train it to sort numbers? I guess it's going to do a good job if you like produce enough training data like for it, right? So what we saw basically with that is that we saw kind of like how these different like concepts which were always there in programming, one way or the other, are landing up into this like machine learning world in neural networks. Right? And I think basically this would also give you some ideas on how basically machine learning may proceed like going forward. Right? So some of the examples I basically give out is that where modern research, I mean, it has been happening for some time, but like I think it will continue to go, is how do we integrate memory into like neural networks? Right. So as of now, we are still kind of like refining our understanding on how do we get memory and processing tied together. So even that advancement, even in digital logic are happening like as we speak, but in machine learning also basically, I think more evolution on basically that will like happen. Right. So my thought basically there was to like give you some of these like thoughts, how these two things are like kind of like paralleling, right, each other, right, to give you some intuition on how basically like neural networks are unfolding as we speak, and they might basically into the future. And also basically I want to show this analogy, like the tricky one, which is that digital logic, on the top of that, we are basically running machine learning, right? But we want basically that machine learning to be smooth. We are treating those variables as analog to be able to find those like gradients, right? So essentially we produce a very interesting mix where humankind started with the analog like circuits like a little bit before digital, right? And then basically digital took over and analog was basically just left to the periphery of like analog to digital conversion for voice, like camera sensors and like whatnot, right? But now we are basically getting to a regime where on the top of digital like logic, we are implementing analog computations, right? So I find it very amusing, and it's also leads to some, I think, some research pointers like how it's going to evolve in the future. And I think that was within my last slide, and I'll be open to like any questions.
Thank you so much, Alec. It was really, really great. Appreciate your presentation. I know I'm in the HR function, but I personally learned about one-hot coding. So thank you so much for that. We've collected some questions from the audience. So I'll take the most popular one. So the first question I have for you is, what determines the number of layers in a deep learning network?
Awesome. I think this is a question you would find answers popularly to in like the existing literature. So I won't talk too much like about it. But basically, as I mentioned, in theory, just 2 layers are actually like enough. What happens is that using just 2 layers, 2 things are hard. One, number of neurons in that layer would tend to grow exponentially with the complexity of the problem space. Right. So just like what we saw throughout this like Cohen-Mikulski algorithm and stuff before, if kind of we are restricting to 2 gates, like number of gates required could become very large, right? So what happens with deep network is that for more complex big problem spaces, basically it helps to basically have like larger number of layers, even though 2 in theory is just like enough. That's really one aspect, right? Second, basically is that for reasons that we don't fully understand yet, right? When we have deep neural networks, training somehow becomes easier. So if kind of you were to train this 2-layer network for the same like problem space, we may find basically like hard time like getting it to be like that, right? So we train deep neural network, and then we can use the deep neural network to somehow like backwards train that 2-layer like network as well, right? So in theory, 2 layers are just like enough. But in practice, basically, we have to take our often judgment calls and experimentation to try to see how many layers we might actually like need. And that again depends on, think of basically like the analogy I gave, right? So if you were to write code for basically that, right? How complex a single function may look like, how many intermediaries may be involved, right? So again, given a problem, estimating what is number of lines of code that would be, right, is kind of basically goes very similarly to that, to basically take, hey, given this problem, how many layers or how many neurons in those layers my deep neural network would ideally like have, right? So that's how basically the analogy is like kind of like deeper than what it like seems, right? But basically little bit of experimentation, right? So just like we may say, hey, like we won't know exactly number of lines of code it may need before we actually fully done with writing that code. We can only estimate. Same thing just happens for deep neural networks too.
No, fair enough. Thanks, Alec, for that answer. I'll move on to the next question. So, in the digital logic resemblance with machine learning, don't you think the digital logic circuits will behave like an overfitting model rather than generalized ML model?
Great question, right? So, and I think that's the like essential point basically there. So when we were synthesizing digital logic, right, the cost functions we gave it were that, hey, for whatever entries we have in those two tables, you must get every single item right. Right. So by very formulating the problem, we are telling it, no, you have to basically fit that data no matter what happens to the unknowns. Right. So by going to machine learning, essentially what we're changing are those cost functions where we are relaxing to those. We're saying, hey, don't fit that like data perfectly, because your goal is to basically do a better job at those like unseen basically like inputs. Right. So that's I think is the trick. Right. So we still had training data in like digital logic, but just how we optimize things basically format to prevent that overfitting as basically like is being asked. It is exactly what is the big difference, core difference. Right. So and that's what basically leads to system basically being able to use those iterative methods, because if you were to tell it, hey, for every single input that's in the training data, you must fit perfectly, well, then we are back to those like NP complete algorithms.
Yeah, and I think you touched upon this, I think, for the last question, which is, what is the effect of training data quality on the model performance, especially for the attention example that you mentioned?
Right. Great. So for attention in particular, I may not basically know the like answer, but in general, I can talk about it. Right. So training data quality has like many different like aspects. One is like, does it have enough coverage to see basically what we might expect? As an example, if I have to detect face versus not, right, and I had no training example whatsoever where somebody is wearing sunglasses, right, system may not work well. So that's basically one aspect of like training data quality. Second basically aspect is, are there noisy labels? As in basically, is it that basically somebody is actually like wearing sunglasses in the face? It's actually a face, but in the training data, we call it not a face and so on, right? So basically what has been shown is that this is a little bit counterintuitive. I don't have like full basically mathematical like notion behind why that is, but feeding wrong data like goes on to hurt the system more than having less data. Right. Okay. So basically, like what we want to do in terms of quality, we do want to have enough like coverage, as an example, for different ethnicities or different basically types of like lighting conditions and like so on, depending on what problem we are talking about. Right. But basically having exhaustive coverage like helps, but feeding wrong data actually goes on to hurt disproportionately. Right. So basically, I think trying to get those labels right becomes like important, but there are ways like active learning out, which we can help with that too.
Okay. No, lots to learn from you, Alec. Thank you so much. These were the questions that we had from the audience. And again, thank you very much for being part of the AmTech conference with us and being here live doing the session with us. It was absolutely wonderful. So thanks again for being our first session for today.
So if there are further questions, feel free to like reach out to me like offline. So that would be like work out. And it's a pleasure for me as well to be here and presenting this topic to you. Thanks to everyone for organizing as well as like joining.
Fantastic. Thanks a lot, Alec. And I know we have the next session as well. So in less than 20 minutes, we have another session where Amazon speaks Arabic. So you can join early because we have some videos and trivia questions for our next session. Thanks again, Alec, and thanks again, everyone, for joining this session.
Thanks, everyone.